Okay, let's get started on the gravity worksheet. It says find the field strength of the Earth's gravitational field 1,000 kilometers above the surface. So, right that spot right there, you want to know the field strength. Well, there's not even anything there. But with a field strength, it's always a 1 kilogram test object. So you could say field strength is Gm over r squared. There's only one mass because it's the mass of the planet. The mass is a test one, so you could imagine there's a 1 there. Okay, but let's find the radius here. I got to find the distance out. The Earth is 6,380,000 meters is the radius. And this thing is another 1,000 kilometers up. And that will be our radius. So we got 6,380,000 plus another million. Gives us 7,380,000. So 6.67 times 10 to the minus 11. Earth is 5.98 times 10 to the 24 kilograms. That's all going to be on top of this number squared. And this will give us gravitational strength. At that distance, on the Earth, it's 9.8. We'll see what it is here. 5.98 exponent 24 and 6.67 exponent, change that to 11. I got 7.32. That's newtons per kilogram. So even 1,000 kilometers up in there, the gravity's still pretty strong. But you feel weightless on those space stations because there's no normal force. Okay, I got two spaceships. I used to draw a picture of them. And they are 250 meters apart. One guy weighs 12,000 kilograms. And the other guy weighs 8,000 kilograms. And they want to find the force of attraction between them. Force of gravity. This is the universal equation for gravity between anything. The moon, the sun, two atoms. It's for everything. So we're just going to fill in the masses. The other mass divided by the distance of separation squared. And this will give us our answer in newtons. So 6.67 times 10 to the minus 11 times 12,000 times 8,000. And then divided by 250 squared. And we change it to scientific notation. Times 10 to the minus 7 newtons. Not a lot of force. These things will not accelerate very quickly towards each other. But don't forget, an hour is 3,600 seconds. So if I was accelerating for that long, they would pick up a little bit of speed. It wouldn't take them too long to crush towards each other. Okay, the next one says, find the potential energy, 400 kilogram rock at rest, 10,000 kilometers above the surface. Okay, we'd love to use EG equals mgh, but that's only where G is constant. We already know that 1,000 kilometers up, the G's already dropped. It dropped down to 7.3, so that's not going to work. We're going to have to use our universal gravity equation. Negative G m1 m2 over r. Same formula except it's not squared at the bottom. It's negative because we said really, really far away is your reference point. You have no potential energy when you're super far away from everything. So say the sun. As you fall towards the sun, you lose potential energy, but if you start with 0, all your answers are going to be negative. Most of the time, we're just looking for the difference between them, though. So, but R still measured from the center. So 10,000 kilometers plus 6. That's the radius of the Earth. 6,380 kilometers, and this is 10,000 kilometers up. We're going to add that up to get the radius, and we can stick that in there. So 6.67 times 10 to the minus 11, mass of 1, let's put in the Earth, and 400 kilogram rock, and that's going to be divided by the sum of this, 6. Let's get back to, so 6,380,000 plus 10 million. Gives me 16. Let's get the math done then. 6.67 16,380. I might want to put that in scientific notation again. 9.74 times 10 to the 9 joules. Okay, that's the potential energy. Well, it's way up in the air. It's a big number. Okay, you could try the other one, mgh, but that's using a reference of the ground. Really need to find it on the ground, and then we'll be able to see what the difference was. Okay, this is going to be same numbers again on the top. And that's 5.98. That's a 400 kilogram rock. And you're sitting on the ground, which means you're still 6,380,000 meters from the center. 6.67 minus 11, 5.98, exponent 24, 400, and then 638. That's 2.5 times 10 to the 10 joules. As you can see, we've dropped lower down the negatives. Okay, so we've dropped down even lower into the negative. You come closer to the surface. This is how much energy it would take to get yourself totally out into space if you could just fly away. Okay, so then next question. What's the change in potential energy of the rock? So we're just going to find delta EG would be like final minus initial. Okay, but you're subtracting a negative, or just, even if you ignored the negative sign, just take a look at the difference between the numbers. 9.74, that, a difference of 1.53 times 10 to the 10 joules. That's how much energy shifting those two positions. How fast would the rock be going? Well, when you're on the ground, totally kinetic energy. mv squared over 2 of the rock will be this much energy. Because it had this much at the top, had that much on the ground. The difference between them has been converted 100% into kinetic energy. So let's write this out. So 1.53 times 10 to the 10 equals 400 v squared over 2. And that number's still on my screen, times 2 divided by 400, square root. I think I'll go back to regular notation. Okay, 8,736 meters per second. That rock's flying. Okay, if you went back and did E equals mgh, so if we took a mass of a rock times 9.8 times the height was 10,000 meters, 10,000 kilometers. So that comes up to 3.92 times 10 to the 10, which is more than double this, because as you go higher and higher and higher, the force got less. So you can't just use mgh because g doesn't stay at 9.8. So you would get a much faster speed if g stayed constant, but it's still fast, but it's gonna be slower though. Okay, what's the gravitational field strength on the moon? So we're back to g again, equals g m over r squared. And there's only one m because we're just looking at the moon. So 6.67 times 10 to the minus 11. And I need the mass of the moon, here it is, 7.35 times 10 to the 22. I need the radius of the moon in meters. And let's find out how high we can jump on the moon. 6.67 exponent minus 11, 7.35 exponent 22. And then I got 1737, 1, 2, 3 zeros, squared. And we got 1.62 newtons per kilogram. Or the acceleration on the moon is 1.62 times, 1.62 meters per second squared. Okay, it's about 6 times lighter. The radius of the moon's orbit. Okay, so we got Earth, we got Moon. And the radius of the orbit is 385,000 kilometers. I said, determine the force of the gravity on the moon, on the earth. This is what creates the tides and things. So we got to find out force of gravity equals G, M1, M2, all over R squared. So we got to go 6.67 times 10 to the minus 11. Mass of the earth is 5.98 times 10 to the 24. And the mass of the moon, was given in the last question, 7.35 times 10 to the 22. And the separation is 385,000 kilometers. Change that to meters, square that. And let's find the force that's holding the moon in orbit. 5.98 exponent 24, 7.35 times, and then we're going to divide by 385 million squared. We get 1.98 times 10 to the 20 newtons of force holding the moon in the orbit and also pulling on the Earth too. Okay.